Hey, what's up, guys? I think I've talked about making another video about Celnav for our campaign. Uh, I was originally going to do one about the noon site itself, meaning getting latitude at noon and then getting longitude at noon, but in real life, that's actually not really used very much because it's difficult to determine the exact time of when noon actually occurs because the sun tends to hang at its highest altitude for a while, and so it's hard to determine exactly when that point is. And so, what I've decided to do instead is teach you guys how to do a running fix. And so, you might be asked in the campaign to do a running fix instead of like a morning or an evening star site, like if the weather is bad at those other times. Like, say, for example, you want to fix during the day. I'm going to try for a morning site for you guys, but if you can't get a morning site, the next alternative is a running fix during the day, before the evening, obviously. So how this works is, you may be familiar with the concept of running fix. If you're not, what a running fix is, it's less accurate than a true fix. You're trying to get, for a fix, you need at least two bearings, right, that are crossing. Well, what you're doing with a running fix is you're using the fact that the sun moves quickly across the horizon during the day. So you'd take a site in the morning when the sun is at a certain azimuth, and then you would allow at least 2-3 hours to elapse, and then you'd take another line of position of the sun at that point in time. It's going to be, the azimuth is going to be enough where you're going to get a decent crossing. And what you do is you take that first line of position and you advance it to the second line of position. You dead reckon that line of position forward, using time, speed, and distance, and then where those cross is your running fix. Okay, running fixes are typically done for like when you're for piloting, piloting a boat, for example, using land bearings. That's typically where you see the concept of running fixes. I shoot a lighthouse over here, and then I'm over here, and I shoot the lighthouse here. I advance that first line of position up, and where it crosses the second one, that's where I'm at. But it's subject to your DR error, right? So that's why it's not quite as perfect solution. But honestly, I mean, from what I understand, I mean, you can really get by with just doing running fixes in real life. But so the I'm not going to have you advance. I'm going to show you a shortcut way to do it. So really what you're doing is you're reducing two sites. There's one site in the morning, one site in the afternoon. You get your data for each of those sites, and then you actually we'll just plot from the DR position of this last site, and it's going to work out. Instead of having to do all the advancing and all that stuff, you can just plot both sites from this last DR and call it a day. So I'm going to assume for the first part of this video that we went into the website or into my spreadsheet and got all the data we needed, and got our computed height and azimuth for both of these sites, and then the intercepts, and go how to plot them. But just to start with, this is the almanac data for the sun. We're going to assume November 19th, 39. We're going to say that we took our first site at 1000. The GHA of the sun at that hour, since it's on the hour, we don't need to interpolate. It's 333 degrees, 40.7 minutes. Okay. The declination, the sun is obviously south, and it's 19 degrees, 18 minutes. Okay, so you need that for your site reduction. At 1300, now the second site we took, let's just assume, and our DR position is here. Okay. We took 12 degrees, 51 minutes was our sextant reading, observed height. Our DR position was 55 degrees, 40 minutes north, 44 degrees, 30 minutes east. All right. Second site we took at 1330. So I can see that's 3.5 hours that have elapsed. That's going to be enough time for the sun to have changed position. Okay. So we're going to assume 1330. Observed height was 10 degrees, 22 minutes there. DR position was here. And we arrived at these data from our site reduction. But just so that, we're clear on how I'm going to just go through the interpolation tables again, because that's sometimes confusing. So the 1000 site we don't need, we're done. 333, 40.7 is the GHA, nothing to do there. For the 1330 site, however, since the almanac just shows our numbers, at 1300 the GHA, the sun is 18 degrees, 40.4 minutes. All right, well, we need to know what it is for 1330, right? So we go to our handy dandy increments and corrections table. Here are the sun increments. We read down at, we got 30 minutes that we need to account for. So 30, it's 7 degrees, 30 minutes is what we need to add to the 1300 GHA. So how we do this is pretty easy. We would say 18, and again, there's been some confusion about the DMS and degree buttons on a calculator. I'm telling you, just add the minutes and degrees. It'll be much easier, and this is how you do it. You just take 18 degrees, 40.4, that's at the hour, right? Plus 7 degrees, 30 minutes is, I know I'm going to be over 60 here, so I'm going to add 1 to the degrees. So I know this is going to be 26 degrees and 10.4. In other words, I would have gotten 25 degrees and 70.4, but since I'm over, I need to subtract 60 and add 1 here. Okay, so 26, 10.4, that would be the GHA that you would put into either the spreadsheet or the website for the GHA of the sun, right? Interpolated there. Okay, so that's that. So again, I'm going to assume for this that I've already obtained this data automatically from the website, but I am, as a bonus in this video, aren't you lucky, going to show you how to do it on a scientific calculator. It's very easy once you know the formulas. Okay, so if you don't want that piece, you can forget it after I say we're done, but if you want that, stick around and I'll show you how to do this, how to do these pieces here using a scientific calculator, reducing the sites using a scientific calculator. Okay, so all right, so the first one, so this is how this would go down. Okay, you'd say, okay, you're going to do a running fix today. Here's your first site, time, observed altitude, and then your DR position to start with. Okay, and then I won't give you the second DR position, but I will give you the time and the sextant reading of the second one. You will know based on the time difference, you're traveling at 6 knots, or honestly in a type, you're type 9. If you're in a type 9 or type 7, you're going to be at 7 to 8 knots ish, but you will be, I will let you know what your cruising speed is. Okay, so then you can do the math and time, speed, distance, figure out what your second DR position is. Okay, so you get your first DR position, second DR position, you have this noted. Okay, what you're going to do is you're going to reduce both sites using both sites' data. Okay, you're going to get your computed height and therefore your intercept as well as your azimuth for both sites independently. And then what you're going to do for plotting, instead of plotting both and then advancing this one, you're just going to plot both of them from this DR position here, the second one. Okay, so that's why on here you can see I've already got this 55 degrees, 51 minutes north. The plotting sheet's already set up. 5 degrees, 2 minutes east. So it's already set up for the second DR position. Okay? Okay, so that's pretty straightforward. So then, again, and this should be familiar. I'm going to plot the first site. Azimuth is 159 and it's 4 toward. So let's do that. Okay, that's the 1000 one. Right, but we're plotting it from the second DR position, right? But that's the 1000 one, first one. Okay, now the second one, what are we at? And to reiterate, why is this +4? Well, because our observed height was greater than, I don't think I put this, but Ho, mo, to. Maybe I did. I don't know. But in the last one, ho, mo, to. Ho, ho, more, toward. But the easiest thing to do is just to reason your way through it. Just like in range finding in Wolfpack or whatever, the greater the angle that you're measuring in your scope, the closer the target. Therefore, the greater the angle of the body that you're seeing, the closer you are to that body. Okay, so HO is greater than HC by 4, so it's plus 4. HO is greater than HC by 3 here, so it's plus 3. Okay, so let's plot the second one. The second one is 210, 3 toward. So let's do that. Again, would be our fix if we were, if we weren't on if we were not on a flat Earth here, that would be our fix. But we're on a flat Earth, so we need to correct for the minutes of longitudes. Again, this is 2 nautical miles east of 2, so it's going to be 5 degrees and 4 minutes east. So our fix is actually going to be, and then what do we have for latitude? We got 51, 50, 49, 48, 47. Okay, so we got 55 degrees and 47 minutes north. Okay, always just round to the closest minute. There's no need to do decimals of minutes or anything like that. It's close enough because you have to consider that, a minute is a nautical mile, okay? A minute of latitude is a nautical mile. A minute of longitude is a nautical mile at the equator, but we're at 56 degrees north here. So, I mean, a minute of longitude is, it's the, whatever the cosine of the latitude is times the minutes, or times the miles, excuse me. So it's much less than that. So, I mean, if you think about it, it's okay, you're going to be off at the maximum, you're going to be off by 1 mile. Well, at sea, 1 nautical mile is just under 2,000 meters. You're definitely going to be okay. So anyway, so that we know that is 55:47 north. And then we measured that this was 2. So we have to go 2 east of that. So it's 5 degrees and 4 minutes east. Okay, that's our fix. That's our running fix. That's as easy as it. That's as hard as it gets. It's pretty easy. To reiterate, a lot of times when you look up how to do a running fix, they teach you how to do. You plot your first one. So we actually came up this way. So I figured our boat was going a course of 058, coming up from a DR position of 5540 down here. And 430, okay? And we went our way up here. And then, a lot of times they teach you, you plot your first line of position down here, okay? And then you dead reckon up here, and you plot your second line of position up here, and then you dead reckon your first one, up. But the problem with that is when we're doing it on graph paper, we're on a flat Earth. So the dead reckoning doesn't work because the second, what do you actually advance it by? Because the dead reckoning is not going to work because your minutes of longitude are not going to be the same for your DR positions, or they're not going to be accurate because you'd have to do that cosine math. So the easiest way to do it on graph paper is to just plot everything from the second DR position like we did, and you're going to arrive at the same answer. Okay, it's a shortcut. So anyway, so that's our fix right there. That's what we would take to the map and plot it. Again, just use whole minutes, and leave the decimals out of it. So with that, that's pretty much it. The only thing I will add then is that you would, you'd be considered probably good for the day. 13:30, you got your sight for the day, so there's no reason to wait for an evening sight. This is probably sufficient for your fix for the day, okay? But so the priority, when you wake up in the morning and you try to get your morning sight To the extent you can't get a morning sight, then I will give you a running fix to do, and then you'll be good for the running fix. Worst push comes to shove, then you do an evening sight if you can't get either one of those. Okay. Now that people are moving up in boats and they're going out on longer patrols, it's not going to be just this jaunt up the North Sea, this straight course. Boop, here's Helgoland where you leave your escort, and you just shoot on up to your patrol grid and then just shoot straight back again. Now it's going to be, I'm going to shoot up to Orkneys, and now I got to make a turn and come around, and then I got to make a turn, another turn again to get into the North Atlantic or whatever. You're going to have several turns, so you're going to actually want to know roughly where you are sometimes in order to A, avoid islands, and B, know where to turn. So it's going to be a little more interesting. You're going to might want to get a fix at a particular time of day, etc. Okay, so hopefully that's clear. So that's the end of this portion here. If you want to cut it off there and say I'm good, please do so. Otherwise, the calculator, I'll start the calculator stuff now. We won't plot anymore. We'll just switch gears to the calculator. Okay. All right. So the way the calculator works is, and by the way, here's the actual fix. So the actual at the first site was this 5537. I simulated some DR error here. 5537 versus 5540, 430, 435. So we're actually a little southeast. Okay, in actuality, we're a little southeast, and then where we started. We didn't know, right? We didn't know. It was DR. It was not perfect. The second DR position was 51 versus 46. So again, we're still south. In actuality, we're still south. And 52, 56, we're still southeast. So then if I look at where we landed, 5547, okay, where we ended up a little north. So that actually corrected the running fix corrected our latitude pretty well. We're only a minute off of our true latitude. Okay, a mile off of our true latitude. It got us closer on the longitude by 2 minutes. Okay, so you can see, there is a little bit of still inaccuracy because of the inaccuracy in the DR, but because these sites weren't taken simultaneously, so there's going to be a little inaccuracy there. But again, you can see the running fix refined that, and that's the whole point. Okay, so anyway, so that's that. So the calculator, what you want to do for the calculator is, obviously you need a scientific calculator with trigonometric functions on it. Okay, sine and cosine primarily. Okay, and then you also want the functionality of memory slots. So I would say most modern scientific calculators, not Windows 10 calculator has several memory slots, but Windows 7 calculator apparently does not. But anyway, if you're using a store-bought calculator like this, you might have these store and recall buttons here, but then make sure you have 3 memory slots that correspond to those, because you're going to have 3 things that you're going to have saved at any one time. All right, so most of the terms you're going to be familiar with already from the website, but basically what you want to do is, the 3 things you need are LHA, which stands for local hour angle. You need declination, which we know what that is already and know how to get it. And you need, in fact, hold on, I'm going to write these in a different order because that's how we'll store them. You need your own latitude. You need declination. And you need local hour angle. Local hour angle, not GHA. This is local hour angle, which is a little different. It's adjusted for your latitude, your longitude, right? So latitude, declination, and local hour angle. Those are the 3 things you're going to store, right? So let's start storing them now. So let's do the first site. The first site, the latitude, the DR latitude is 5551. All right, so again, you need to know how to do, so 5551, I do 55.51, okay, and then I push, I get that into decimal degrees, which is 55.85, and I'm going to store that in the first slot, store 1, okay. The next thing I'm going to do is I'm going to put the declination in. At 1000, the declination was a negative, south, use negative 19 degrees 18 minutes. So I'm gonna say 19.18, but I need to convert that to decimal. Okay, 19.3, make it negative, and then store that in the second memory slot. And we're going to call this one, first one A, call this B, call this C. Okay. So I've got that stored in the second memory slot. Okay. All right. Now I need to compute my local hour angle. How do I do that? Well, it's GHA plus your east longitude if you're east, or minus your west longitude if you're west. We are east, so let's do the math. Very simple. So I take 333 degrees, 40.7 minutes. I know it's east, so I add. So I say plus 430 is 3. That's a 3. Hold on. I know it's going to be greater than 60, so I'm going to add 1. 338 degrees and 10.7 minutes, right? Because I'm left with 10 after I take the 60 out. 338, 10.7. That is our local hour angle, okay? That's the sun, so we don't have SHA to worry about. But if stars, you'd have to do that, right? So anyway, okay, 338. So I'm going to type in 338 point, and that's 10.7. Okay, so it's 0.1042 because 42 is 0.7. 42 divided by 60 is 0.7. Okay, convert that to decimal, and then store that in 3. All right, I've got everything stored. In memory slot 1, I've got the latitude stored. Okay. Oh, you know what? I think I did. Let me make sure I did 55.40 for the latitude. I might have done 55.51. Hold on. Yeah, I did 55.51 by mistake. So, excuse me. I'm glad I caught that. It was 55.40. Okay. Convert that to decimal degrees. Okay, that's our latitude. So 55.40 is saved. The declination at 1000 is 1918. Let's make sure we have that right. Press recall 2. Yep, that's 19.3. That's correct, and it's negative because it's south. All right, and then we've got our local hour angle, which we computed here. The GHA plus, since we're east, our longitude is east, plus our longitude 338, 10.7. Okay, so that's saved in 2. So the formula for azimuth, or excuse me, for computed height, it equals the arc sine, which on your calculator is going to be probably sine minus 1. Okay, so I'll just write it like that, sine minus 1 of, and remember these A, B, and C here. Okay, sine minus 1 of the sine of A times the sine of B plus cosine of A times cosine of B times cosine of C. Okay, and then once you get that, you're gonna take the arc sine of it. Okay, so let's do that. Pretty straightforward. Now, once you got this thing, it's just recalling everything. So I want the sine of A, latitude. So this is, again, A, B, and C. That's why we did this in order. A, lat, dec, LHA, ABC. Okay. So recall 1. Take the sine of that times recall 2. Take the sine of that plus recall 1. Take the cosine times recall 2. Take the cosine times recall 3. Take the cosine equals, and then take the inverse sine, arc sine, second sine. There's your altitude. Now to get that in degrees, this calculator has a degree, since this is in DMS already. Yeah, see the DMS there above the button. I need to press the third there, and now I get it in. So here you go, 12 degrees, 46.9. 12 degrees, 47. That's pretty close, okay? 12 degrees, 46.9. I'm going to go back to decimals. Okay, I would write that down. But then what I'm going to do is I'm going to save that over the LHA because we don't need the LHA anymore. So I'm going to press store 3. So now what I've got is one more here. I've got D is HC, okay? LHA is gone, but let's just call HCD, okay? Now the azimuth formula. So now we still got everything saved in here. Now we're going to do the azimuth formula. It's a little more involved, but it gets you more or less a direct answer, okay? But there's one rule you have to remember, and I'll lay this out. So the azimuth is a fraction, and what it is, ultimately, it's the arc cosine of the numerator is the sine of B minus the sine of D, okay, times the sine of A, okay, over the cosine of D times the cosine of A. And then you're going to take the arc cosine of that, okay? So let's do that, and then we'll talk about the rule. Because, it's going to give you some bearing, but you need to know which way, whether it's going to be north or south, okay? So let's do that. So we've got everything saved in here. Remember, D is now saved in 3. All right, so we're going to take, first we're going to do parentheses. And we're going to say recall B and take the sine of it minus recall D and take the sine of that times recall A, take the sine of that, close parentheses, okay? I'm here now. Now I want to divide, open parentheses, recall D cosine times recall A cosine, close parentheses. Now I'm here. Now I want the answer equals, okay, now I want the inverse cosine of that. Okay, now that is our answer, 159, which we see here, but we don't know that yet, okay? And why we don't know that is, let's just jot this down first of all, 159, okay? Whoa, I don't need that much lead. How about that? We run out of lead right away halfway through the video. Bear with me. That was good timing. you need to compare the answer you just got with the local hour angle that you computed. Okay, so the LHA, so what we just got was 159. Okay, the cutoff is 180. All right, so one will always be less than 180, and one has to be always over 180. And when I say one and the other, I mean LHA and the answer, the azimuth answer. So we got the 159 there. We know that's less than 180, so we know that the the LHA, which was, if we recall, we didn't, it's here, 338. Well, that's over 180, okay? So we know that the azimuth that we got has to be less than 180. If it weren't, let's say that this were less than 180. Well, this is also less than 180. How do we make this greater than 180? We take 360 minus that. That's how you know to get the true azimuth. Is you say, okay, my calculator gave me 159. Where was my LHA at? LHA was greater than 180, so then 159 is good because that's less than 180. If LHA is on the same side of 180 as azimuth, then I need to take azimuth out of 360 and get an answer that's over that's over 180. Okay. That's over 180. Okay, so that takes care of that one. I don't need to do the second site. That it's the same process. Okay. You're taking your GHA and converting it, making it into LHA by adding your east longitude or subtracting your west longitude, right? And then you're plunking these items into the calculator, and then you're applying these formulas here. Okay, so those are the formulas you need for the two things to do them with a scientific calculator, right? And get you the same answer. And I'm telling you, it's very quick once you learn how to do it. So that's that. So let me know if you guys have any questions about that. That's pretty much the long and short of it. As far as Celnav goes in our campaign, between the star fixes that we already went over, plus the running fixes, that's pretty much all we're going to do, I think, for that. So anyway, I'll talk to you guys soon.